This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 3 of Week 5, Steam Turbines. A turbine turns a drop in enthalpy into shaft work. We set the ideal isentropic limit from the steam tables, then scale it down with isentropic efficiency to find the real work and the real exit state, including the moisture that erodes blades. A turbine converts a drop in enthalpy into shaft work. Inlet enthalpy minus exit enthalpy times mass flow. The best it could ever do is a reversible adiabatic expansion, meaning constant entropy from inlet to exit. That ideal exit is state 2s, found at the exit pressure where entropy equals the inlet entropy. The isentropic work, Hn minus H2s, is the ceiling. A real turbine always falls short of it. Real expansion has friction, so the actual exit enthalpy sits above the ideal one at the same exit pressure. Isentropic efficiency is the real enthalpy drop over the ideal drop. Eta T equals Hn minus Hout all over Hn minus H2s. For a turbine, the actual drop is smaller, so efficiency is below 1, typically 85 to 92% for large utility turbines. Watch the direction. Turbines are actual over ideal. Pumps and compressors flip it to ideal over actual. The variable table for a turbine problem. Inlet enthalpy and entropy come from the superheated steam table. The ideal exit enthalpy, H2s, you solve at constant entropy. The actual exit enthalpy follows from efficiency. Exit quality comes from the actual enthalpy. And the saturation properties at the exit pressure, HF, HFG, SF, SFG, come from the pressure table. The inlet state and exit pressure are given. Everything else is a lookup or a short calculation. Here is the recipe for the ideal exit enthalpy. 1. Read the inlet entropy from the superheated table. 2. Go to the exit pressure and set the exit entropy equal to it. If it falls between SF and SG, the ideal exit is wet. 3. Back out the ideal quality from entropy, Sn minus SF over SFG. 4. Build the ideal enthalpy, HF plus that quality times HFG. The key trap, ideal quality comes from entropy, not enthalpy, because the ideal process is defined by constant entropy. Once you have the ideal drop, rearrange the efficiency definition to get the actual exit enthalpy directly, Hn minus eta T times the ideal drop. Then back out the actual exit quality from enthalpy this time, since you now know Hout. That quality is a design gate. Liquid droplets erode the last blades, so steam turbines hold exit quality around 0.88 or higher. Fall below it and you add reheat or more inlet superheat. Note the actual quality is always higher than the ideal quality, because the real exit carries more entropy. Worked problem. Superheated steam enters at 6 megapascals and 500 degrees Celsius. Expands to 50 kilopascals with an isentropic efficiency of 0.85. Find the actual specific work and the actual exit quality. The plan? Read the inlet state from the superheated table, find the ideal exit at constant entropy and 50 kilopascals, scale the ideal work by efficiency, then get the actual exit enthalpy and quality, and check the moisture limit. First, the inlet. The SI superheated table has no 6 megapascal column, so interpolate the 500 degree row between 5 and 7 megapascals. Inlet enthalpy about 3423 kilojoules per kilogram. Inlet entropy 6.89. At 50 kilopascals, the inlet entropy falls between SF and SG, so the ideal exit is wet. Ideal quality is Sn minus SF over SFG, about 0.892. Ideal exit enthalpy is 2396, so the ideal drop is about 1027 kilojoules per kilogram. Now scale by efficiency. Actual work is 0.85 times the ideal 1027, about 873 kilojoules per kilogram. Actual exit enthalpy is the inlet minus that work, about 2550. Back out the actual quality from enthalpy, Hout minus HF over HFG, about 0.96. That clears the 0.88 blade erosion limit, so the expansion is viable. And as expected, the actual quality 0.96 sits above the ideal 0.892. Irreversibility leaves the steam drier. 4 traps. 1. Confusing the ideal and actual exit. State 2S is at constant entropy. The actual sits higher. 2. Finding the ideal quality from enthalpy. The ideal quality comes from entropy. Only the actual quality comes from enthalpy. 3. Flipping the efficiency ratio. Turbines are actual over ideal. Pumps and compressors invert it. 4. Skipping the moisture check. A clean work number with exit quality below about 0.88 is not a viable design. Always report the quality and compare it to the limit. Bookmark the turbine pages. Turbine work is mass flow times the enthalpy drop. Isentropic efficiency is actual drop over ideal drop. The actual exit is the inlet minus efficiency times the ideal drop. Read the inlet from the superheated table, interpolating between columns, and get the saturation properties at the exit pressure from the pressure table. Ideal quality from entropy, actual quality from enthalpy. The whole problem is 2 tables and 3 formulas. You now own the turbine. Set the isentropic ceiling, scale it by efficiency for the real work, and read the exit quality to confirm the blades survive. In topic 4, we run the same logic the other direction. Compressors add work to a gas, and the efficiency ratio flips to ideal over actual. Same steam table fluency, same isentropic baseline. We just push energy in instead of pulling it out. Carry today's habit of separating the ideal state from the actual one.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.